Welcome to the office. I want to take a look at a couple of examples of direct products, so groups. And in this case, we are going to look at a couple of groups that are abelian, so z sub something here, right? Integers modulo our favorite numbers. So we're going to look at z2 cross z6 and z4 cross z3. You'll notice that each of these has 12 elements in them. Z2 cross Z6 has 12 elements. Z4 cross Z3 has 12 elements. I'm actually going to consider this second example first. And we want to take a look at this and decide if the group appears to be cyclic. Now, if you wanted to, you could list all of the elements in this group. So Z4 cross Z3. We won't always list all of the elements. In fact, definitely don't want to do this in general because we're going to be working with much larger groups, much larger cross products or direct products rather. Let's do it here though, at least one more time. So I want to take things that belong in here and things that belong in here. So 0, 0, 0, 1, 0, 2. That cuts us all the way through Z3 in that second entry. 1, 0, 1, 1, 1, 2. That gets us all the way through Z3 with ones in the first entry. 2, 0, 2, 1, 2, 2. And then finally 3, 0, 3, 1, 3, 2. Excellent. That is our 3, 6, 9, 12 elements of this set. And the question is, does it appear to be cyclic? Well, essentially, in order to answer that question, we just, if it is, we just have to identify a generator. So cool, no big deal. Well, Z4 is generated by 1 and Z3 is generated by 1. So I'm going to take a look at what's generated by 1, 1. Well, what's generated by 1, 1, of course, I can take, well, we could list these out each, but let's take this 1, 1 and add it to itself. So 2 times 1, 1 is 1, 1 plus 1, 1. Well, that's 1 plus 1 and 1 plus 1. So that's 2, 2. Fantastic. I could take that element, so I can think of it as 3 times 1, 1, which is 2 times, I'm sorry, that's 2, 2 plus 1, 1. Because I already know that 1, 1 plus 1, 1 is this. So then I can add another one to get the third. So that's 2 plus 1 and 2 plus 1, no big deal. 2 plus 1 modulo 4. Oh, and oh yeah, no, that's good. Okay. 2 plus 1 modulo 4 is 3, so that looks good. 2 plus 1 modulo 3 is 0. No big deal. That sounds great. All right, so we have what the two of them together give. Of course, 1, 1 itself is just 1, 1. So that's in the set. This is in the set. That's in the set. All right, the subgroup or the group, whatever it turns out to be. And 4 times 1, 1 is, I can certainly think of this as 4 times 1 and 4 times 1. In the case of the first, that gives us 0. In the case of the second, that brings us back to 1. 5 times 1, 1 is going to give us 5 times 1, 5 times 1. 5 modulo 4 is 1. 5 modulo 3 is 2. 6, 1, 1 is 6, 6. Okay, so I'm just abbreviating the notations now, and 5 times 1 is 5. But 6 modulo 4 is 2. 6 modulo 3 is 0. So 7, 1, 1 is 7, 7, but that is actually, now let's see here, 7 mod 4 is 3, 7 mod 3 is 1, 8, 1, 1 is 8, 8, so that's 0, 2, 9, 1, 1. Now, based on our previous section, in order for us to have a subgroup, we know that the order of that subgroup must divide the order of the group itself. That means that the order of 1, 1 could either have been 1, 2, 3, 4, 6, or the next thing that it could be is the entirety of the group at 12. Okay, the only thing that makes sense at this point is for 1, 1 to generate the whole group. And we don't have to complete it because we know that the order of 1, 1 is more than 6. The only thing left as a possibility is that the order of 1, 1 is 12. So 1, 1 generates the group. Yay! So once I get to here, the order of the element, actually, before I even get there, once I get here, order of 1, 1 must be greater than 6, but must also divide 12, the order of the group. So the order of 1, 1 must be 12, generating the whole group. Okay, so we could continue on what these are, but there's no real significant need to. And I think that we have the right idea at this point on what it looks like to add in Z4 cross Z3 and do repeated addition. We can still use that multiplication notation for repeated addition, and that is absolutely fine. So we know that 1, 1 generates the whole group, and this is why. Fantastic. So does the same thing hold true here in Z2 cross Z6? This also has order 12, so Z2 cross Z6, or has, the cardinality of that set is 12. The order of that group then is 12, the number of elements in it. So I want to see if 1, 1 generates the whole group. All right, so what does this generate? Well, of course, 1, 1 is in there, and I can actually take 0 times that. So I know 0, 0 is in there. I know 1, 1 is in there because 0 times 1, 1 is just 0, 0. 1 times 1, 1 is just 1, 1. 2 times 1, 1 is just 2, 2, right? Nothing crazy yet. 2, 2. Excellent. 3 times 1, 1 is going to give us 3. Oh, actually, you know what? This is Z2 cross Z6. I was in my mind here thinking that we were still in Z3 cross Z4. So this is not 2, 2. That's 0, 2 here. 3, 1, 1 is, let's see here, 3 modulo 2 is 1, 3 mod 6 is still 3. So we have 1, 3. 4, 1, 1 is 4, 4. 4 modulo 2 is 0. 4 modulo 6 is still 4. And 5, 1, 1 is 5 mod 2 is 1. 5 mod 6 is still 5. And then finally, right in there, finally, 6 times 1, 1. 6 mod 2 is 0. 6 mod 6 is also 0. So this gets us 0, 0. That is not the whole thing, right? That is not all of Z2 cross Z6. There's 1, 2, 3, 4, 5, 6, 7 elements there. Oh, no, there's not. Of course, there's not 7 elements. That gets us back to 0, 0. That's a repeat element here at the end. Whew, I was nervous for a second. There we go. So that gets us 6 elements, half of the group, but not all of it. And if this doesn't generate it, is there something else that does? Well, no, there's not. For us to be certain of that, it can be a little bit tough and a little bit annoying. It should make sense to us, though, as well. Okay, because I'm going to get things of order 2, and I'm going to get things of order 2, 3, or 6 here. And I can't then, right, there's not enough difference there for us to be like, all right, well, this one, they don't both end at the same time. It's going to end at the same time. Anything that's order 2 is going to end at 6. Anything that orders 3 is going to end at 6. When I say end, I mean that all it can generate is 3 or 6 different things. So we're going to end up with, right, even if you take that 3 and multiply it by 2 because you don't have them ending at the same time right away, then that still only brings you to 6. They'll both complete their cycles at 6. That doesn't bring us to 12, right? And there's 12 elements. So what are the conditions for our direct products to be cyclic? That's the question. How do we know, or when will we have that these direct products are cyclic? And that's exactly the topic of the next video. So join me back here in the office for determining when direct products are cyclic. See you in a moment.